The broadcast is now starting. All attendees are in listen-only mode.
Good morning. I'm Carly Rogers, CAPSA's Marketing and Education Manager. Welcome to the Many Uses of Copper Alloys webinar, sponsored by ABC Metals. We are pleased to welcome back our presenter, Jim Michel, Manager of Technical Services for the Copper Development Association. Jim has worked in the metals and corrosion industries since 1973, including the copper and brass, zinc, and steel industries. He has held positions in research and development, technical service, product development, market development, and sales development, as well as has operated his own metallurgical consulting business. Additionally, Jim taught metallurgy courses for ASM International for 10 years and joined the Copper Development Association in January 2007. Some of you may have heard Jim's two previous presentations with us, the Introduction to Copper and Copper Alloys and Mill Processing of Copper Alloys presentations. Today's presentation is the third in this webinar series, and while expanding on the information covered in the first two, we'll focus on the many uses of copper alloys in today's modern life. Jim will answer your questions at the conclusion of his presentation. Please submit your questions using the Questions tab on your webinar toolbar. While he will get to those at the end, if you think of a question during the presentation you don't want to forget, feel free to go ahead and submit that. An hour after the presentation ends, you are going to receive a webinar survey. If you would please complete that, we would appreciate it. And at the end of completing the survey will be a link to today's presentation slides. We'll also have a recording of today's webinar. You'll get that via email, and we'll also have it on CAPSA's website and on our YouTube channel. I would now like to turn the presentation over to Jim Michel.
Okay, thank you. I hope everybody can see my screen. Not necessarily because I want to make sure you know who I am, but it might be helpful in viewing the program. And my intent today, after the first two webinars, is to basically focus on cross-referencing properties of copper alloys with uses, typical uses that are things you use almost every day. May not know about them, but typical uses. I thought this might be helpful. We had discussed in the first two webinars, not only in the Introduction to Copper and Copper Alloys, which was done last spring, but mill processing of copper alloys, and you can see the addresses for these on YouTube on the screen. In each of these webinars, I gave examples of the use or somewhat common uses of certain alloys, but in this webinar, we're going to look at them a little deeper, and so let's get into it. I wanted to review quickly, and I did this in the first webinar, the market and usage areas for copper and copper alloys. Let's look at everything in a market segment, and this is, and I might point out, this is 2012 data. The first series of pie charts I used last spring were 2011 data. That was the last full year we had at that time. Not much different, however, in this particular pie chart versus the last one. Building construction industry has 43% of the overall market. Electrical and electronics, 20%. Transportation equipment, 18. Consumer and general products, 12. That's ranges, stoves, things like that. Industrial machinery and equipment, that's plant equipment and machinery you use in a plant to build other things. But if you look at it a different way, as to product, what type of copper or copper alloy material is being used? 53% of the usage is in wire and cable. So a preponderance is electrical in various forms. Sheet strip and plate and foil, flat products, 16%. So that's a significant portion. Rod, bar, and mechanical wire, 14%. Tube, 13%. So in your service centers, when you stock all these products, you can relate back to this earlier slide. It goes into a lot of these different areas. Okay, and then lastly, foundry and powder products are about 3% of the overall market usage. Well, okay, we did talk last time about getting copper alloys into a certain form, and that was mill processing. Well, I emphasized flat rolled products. So these are fabrication methods in a general sense. You can roll it into shape, and we'll look at a couple photos of that. You can draw them into shape, draw the products into shape into primarily wire, but other things. Extrusion, casting, and there's a couple varieties of castings. Forging processes, and stamping processes. There's others that have small segments. We won't talk about those. Now, in the mill processing discussion last fall, we talked about rolling, and in a regular flat rolled products mill, most of the time you go through a hot rolling stage, which is shown on the left, and then a cold rolling segment, which is shown on the right. And that can be broken down into a wide variety of cold rolling stations. You process it at various widths in various size coils until you get down to the exact size or thickness you want, and then you slit it, finish it, and pack it, ship it out the door. Well, if we look at some other manufacturing techniques, drawing. Drawing is the main process you use to take a rod, which is a cast or an originally formed product, and draw that down or process that down into a wire, and then subsequently draw that down into a wide variety of wire sizes, some as thin or thinner than a human hair. These are put into, as you see in the lower right, cable bundles or twisted pairs, or in some instances they're just enclosed individually. But if anybody, and most of us have, worked with electrical wire or electrical cable at various times, you know that inside a cable, no matter whether it's a coaxial cable, a multi-strand cable, or just a home wire wiring system, there are multiple wires there, and some of them are very thin. So this is where your wire comes from. You can also draw down tubing. I don't have that illustration, but tubing can be drawn down in that sense as well. Extrusion. Extrusion is a process, and you have different sizes of a tube or tubing shown on the right. That's all brass. You can make tubing of different inside diameters, different outside diameters, different wall thicknesses, and actually different shapes. And we'll see some of that later in some of the other illustrations. Essentially, extrusion is a process whereby you take a round billet of reasonably large diameter, warm that, and push it through a machine whereby it contains a die, and that die shapes what comes out the other end. I always liken it to squeezing toothpaste out of a tube, whereby if you look, and most of us have children or have had little ones in the house, you buy some kids' toothpastes, they have shapes on the end. You can extrude the toothpaste into a shape like a star. It's exactly what you're doing in extrusion of the product here. Although the toothpaste is cool and this happens to be warm. Well, we're going to talk a little bit about casting, which is not the casting we normally talk about, but getting something into shape. Here we talk about upcasting. That sounds silly, but it's a matter of, and this is wheel upcasting, you pour molten metal, which is shown on the upper right photograph, into a wheel which has a shape in the outside rim, if you will, and as you pour it in there, you turn the wheel around and cool it, and out the other side, up above, as you can see, comes a solid, although very hot, rod of copper or copper alloy. This system works very well for casting rod, and immediately that shape is processed down into some of the finish sizes, possibly, that you see in the lower right. It's also the beginning of wire rod for the eventual production and drawing of electrical wire, copper wire. So it's a very important process. Virtually all the copper wire that's made these days is produced in a variety of this type of casting and then drawing processes. Here's the other casting process. Generally, you pour molten copper alloy into a mold. It can be a sand mold or a semi-permanent mold or a permanent mold like a die casting mold. And you come out with various products. You open the mold, you take out the product, and you do some finishing processes on it, and then you have your finished product. You don't do much else to it. We have a faucet at the upper right. Those are cast many times in a foundry process. A water meter or a water handling device, such as in the lower center, is a casting that is produced and in large quantity. And again, there's fittings and fixtures on the lower right for water handling systems. Not only T's and elbows, but stronger or more larger fittings and fixtures. But the upper center, which we'll talk about a little later, is a ship's propeller. And they're usually rather large. And we'll get to that as far as uses. But that's made not out of copper or brass. That's made out of bronze, so nickel aluminum bronze or aluminum bronze. Forging. Forging is a very ancient process. In fact, it's really the first process that was used by man. And here are, on the left you see a man holding a heated piece of copper alloy in a forging press. And essentially what you're doing is you're warming it and beating on it. And that's the present day version of an anvil and a hammer from a smith, a coppersmith, silversmith, blacksmith. They all did that type of work. And here are some parts on the right that are produced in a semi-automated fashion in a forging process. These happen to be links that are going to end up forming a chain. Stamping. Stamping is a multifunctional type of process and many times multi-stage process, but we show several different types here. In the machine you're looking at in the upper left is a general stamping machine. The dies that go in there have to be high precision. In the lower center are some electronic parts that are stamped in this type of machine. In the lower left are some emblems or key fob type things. Stamping can also be in the upper right, although it's all usually called coining when you apply it to coinage. And here you have U.S. coinage. And in the lower right, stamping can also be where you just place an imprint on something. Well, those are forming processes. I wanted to go back, and here are copper properties, basic properties. And that's why I went from the first slide, which I did mention at that time. I'm trying to cross-reference properties and uses and how you get there. So we have ductility of copper or copper alloys, malleability, ability to be formed, high thermal conductivity, high electrical conductivity. Copper has the highest conductivity of any engineering material. Now, the actual maximum conductivity is on a material is held by silver, but normally we don't make something like circuits out of that or wiring for your house. So copper is the preferred material. If we want to use thermal conductivity, you get heat out of something easily with a metal, and copper is the best. It's easily alloyed, has good corrosion resistance. We'll talk about that in a little while. It's readily available. There's no loss or no lack of copper in the world. And it's highly recyclable. You can melt down what you use today and make something for tomorrow. And it's antimicrobial, and we'll reference that as well. Okay, well, we saw some electrical wiring referenced in one of the earlier slides, and here's a variety of cables, wire types, bundled pairs, individual wires, but with multi-strands like up on the upper left. And this is 53% of the usage of copper and copper alloys, wire and cable. This is a significant amount. Something I could point out is that copper for wiring generally has to be made out of new copper, just to mine and refine copper. Because if you have too many defects in and or impurities in the copper, it doesn't transfer electricity as well. So by and large, wire and cable is made from pure, brand new copper. That's a very significant point. But this can be recycled when it's recycled. into almost any other product. Another use for, and this is alloy 110 copper as well, sometimes this is circuit board foil. Those are those green or other colored boards that form the circuitry in your electronic systems or electrical systems. You find one in your, obviously in your computer, but you find one in your smartphone, in your printer. You find one in your new electronic phone. You find one almost everywhere with a little control system. Open up your home security system, they have a little circuit board there with all the electronics and controls programmed on that board. If you break the board, you break the system. Generally, this is multi-layered, and each layer is copper, and the green or different colors is a plastic, and then they're interconnected and circuitry is added and other devices are put on these boards. But the foil can be 002, 0015 inches thick. Very, very thin. You don't need a lot because the amount of current that you're transferring in a circuit board is very small. Your microamps. Another electronic use of copper alloys, which many of us don't notice or don't see unless we break open a computer tower unit or a laptop unit, are lead frames. A lead frame is a device or a carrier. It's stamped out of a copper alloy most of the time that the little electronic chip sits on. In the instance, you put the chip on there and then encapsulate, like in the very center illustration, you'll see encapsulated parts in plastic. Those are about to be cut apart to make little devices such as in this upper center illustration. But these are progressively formed in a stamping operation. If you look at the lower center, that lead frame has multiple leads. It produces a leg device that is inserted in a circuit board and provides logic or random access memory or various other things for your computer. LEDs are on a circuit board, light emitting diodes. Any other control device is on a circuit board. If you look to the center right, there's a four-sided computer on a chip module board or device. Those usually are the brains of your computer. Another reason that these materials have to be used here, these alloys, these are high copper alloys, is you have to have good electrical conductivity. You have to have some strength because the leads that are bent have to be inserted into a circuit board and then soldered in place. But you also have to have some thermal conductivity because the circuits on the computer chip produce a lot of heat. And this is also the path for heat extraction for those devices. Connectors. Connectors can be of various sizes. You'll see some very big ones up to the upper left and top. some modest size ones in the center and lower left, and some pin connectors in the lower center right. But in the very upper right, you'll see some miniature connectors. Now, what properties are being used here? The properties are multifunctional again. You have to have conductivity. Obviously, you're using this on a wire or a circuit board edge or a device of some type, so you have to have good conductivity, so the alloys have to have reasonable conductivity. You have to have a retention of strength. So if you have to insert the connector multiple times or disconnect and reconnect something, you can't have loss of strength. Another reason you have to have strength and strength over time, many times a connector is one connector is stuck inside another connector and they're sprung together. If that connection circuit or a connection module loses strength, it can lose contact and your circuitry will be less effective. Spring characteristics are very important. So these alloys, C1510 is a phosphor bronze, and the 172, 173, 174 alloys are beryllium coppers. They generally do not lose strength over a period of time that your device would be in use, and sometimes this is multiple years, up to 10 or more. So you have to be very careful. These devices or these connectors are significantly important in providing us communications, not only in your telephone, but making sure your devices continue to work after a period of time. Very significant. In an industrial setting, the connectors in the upper left or upper center are there to connect from a machine or electrical system on a piece of machinery to a piece of bus bar or other heavy-duty electrical connector providing large amount of current to a working device. It also has to be a very high quality and very good material. Well, now we're going to go into a little bit, and we're moving along faster than I thought, but we're going to go into a series of architectural application type situations. Here you see there are a few illustrations that I've provided here. Most of them are architectural hardware or decorative hardware, but some of them have mechanical applications or aspects as well. Your hinge has to stay in place. In this instance, we use brasses, bronzes, copper nickels, and in some instances, nickel silver. Nickel silver is a series of alloys that are copper, nickel, and zinc, and there is silver in color. They look like stainless, but they're copper alloys. In those instances, you wouldn't be able to distinguish between that and a white alloy such as stainless, aluminum, or something else. As you can see in the lower center, there's a series of door entry devices, and one is a silver color. And the left one is brass, and the center two are bronze. So you get variety of finishes, but that is part of the alloy nature. The mechanical aspects come in locking mechanisms, as such in the lower right. Now we normally want long life and durability out of all these products. I know on my house I have brass entry sets, pass sets, and things, and locks. They're very good for years of use. In fact, when I moved in the house, and the house is not new, it's 60-some years old, it had brass fittings and fixtures, which we've replaced in some instances, but some of them are still there. So they are highly durable. Formability is one of the main factors here, The ability of these particular products to be stamped, formed, rolled, or hammered like a blacksmithy into shape. That gives some of the finishes. You see some hammered finishes on the very center hinge, on the pass or lock set in the upper right. That provides some architectural interest in these particular devices. They can be finished different ways as well. Moving along in the architectural or decorative or other areas, we're using brass piping or tubing. And you can see in the upper right an old advertisement for Hungerford brass and copper, fancy pattern brazed brass tubing. Yeah, they're knurled, they're shaped, they're square, they have all kinds of flutings, and they're still produced in those fashions. You can see tubing in the upper left, as we saw it was extruded. You see one of the main uses of these types of products is in the upper center, brass bed, brass railings, brass tubing is used in bars or eating establishments for railings, for handrails, for decorative hardware. And in the upper left center, the dining set is fabricated out of brass tubing. Decorative because of the color. Structural integrity is provided. Then you have railings in the lower left. They're decorative, and they certainly are add some architectural interest to the structure that is shown there. But one of the things many people don't understand or don't see are musical instruments. We know we see them when our kids are in a band or we're in a band. In the brass section, here's a trumpet, and a lot of other horns are made out of different copper and copper alloys. This particular instrument happens to be a brass, but if you buy a cornet, it'll be a silver alloy. If you buy a French horn, it'll be a different alloy. If you buy a tuba, it'll most likely be a brass. So all of those materials are used in musical instruments. Longevity in those instruments is very important. Here again is decorative hardware made out of nickel, silver, and bronzes. This is, in this particular illustration, these are highly decorative hardware as opposed to the more functional ones we had 2 illustrations ago. You can see the amount of decorative interest that can be developed in a product, not only in forming, and some of these are cast into shape, but others are wrought into shape. In other words, they're forged or hammered or made in other ways. And in the lower right, there's silver color. That's a nickel-silver alloy. So these have been made for decades, millennia actually. So finish is important, forming quality when you have these intricate details, casting characteristics of the alloy. You have to be able to produce a Class A finish in the casting with these materials, and brass, bronze has done that over the ages. Another area which most people don't think about the use of copper alloys in is ship's propellers. And now I'm not talking about the little fishing boat that you take out on the weekend. I'm talking about large ships. As you can see in these illustrations, with the men standing there, these are very large ocean-going ships of quite large size. All of these are nickel, aluminum, bronze, or aluminum, bronze. Those are the preferred materials for ships' propellers in every naval fleet in the world. There are ships' propellers, obviously, in civilian use that are made out of the same materials, but fail-safe situations require that the military have very good propellers as well as other equipment, and we'll get to some of that in a minute. These are all cast, so they must be strong. They must be corrosion resistant. They must be machinable, because once you get them out of the casting, you have to finish machining them. And they must be cavitation resistant. There's a corrosion problem called cavitation that happens on many propellers that causes them to fail. That's one of the main reasons why these bronzes are used for these propeller operations or applications. Another use, and this is seawater piping. This is alloy 706 at 9010 copper nickel. Seawater piping is predominantly in military applications on ships, and all military ships worldwide specify copper nickel piping. Seawater corrosion resistance is the main issue here. Fail-safe condition is important. But you also use these in desalination plants, as seen in several of these photos. You have them on offshore oil platforms or offshore drilling platforms. You have them in other instances like offshore drilling ships. Corrosion resistance, weldability, flowing seawater resistance is significant here, where you don't want corrosion through at a bend or something, and copper nickel is the best material for this. Auxiliary to this are heat exchangers for seawater applications. Most of the time those pieces of piping or tubing are connected to heat exchangers, not only on a ship or a platform, but in a desalination plant or something like that. Again, you cannot have these fail because of corrosion, seawater corrosion, and flowing seawater corrosion. Very important. The next application, well, let me back up. There's two alloys used in these heat exchangers. One is 9010 copper nickel. The other is 7030 copper nickel. 7030 is the preferred alloy for those. Roofing applications, architectural applications of copper and copper alloys are not all alloy 110 pure copper. Sometimes they're brasses, Muntz metal, there can be copper nickel elements which have been introduced recently. There have been nickel silver elements. There have been others, but the predominant use in architectural applications for roofs and flashing and facades and things like that is pure copper. The formability is the big factor. Longevity is a big factor. Soldering or weldability. A lot of these pieces are welded these days so that they have an even finish. If these elements are placed in service and done well and maintained, many of these can last 100 years or more, such as on a university library, on a public building in New York, Kansas City, San Francisco, or on a cathedral someplace, or even on your bay window in your house. Maintenance is important, keeping debris off, and keeping it clean. I wanted to bring up, although most people on this call and don't have statuary sitting in their yard. They don't, but we see it. It's in public places, it's in public buildings, it's on public display. Occasionally we own a piece of sculpture, usually small size for our homes of various types. We, however, usually own bronze. 3 of these statues, the left 2 and the far right one, are bronze. Bronze was, let me back up, in my history lesson, copper was discovered or begun to be used as pure copper in around 10,000 BC. Bronze was discovered somewhat by accident, I believe, around 3000 BC, leading to the Bronze Age. The statuary in those 3 that I pointed out are bronze, traditional bronze, which is a copper tin alloy. It weathers well, can last for hundreds of years, thousands of years in the ambient environment. The 4th statue here is the Statue of Liberty. That is pure copper. It is made differently than the others. The others were cast into shape. The Statue of Liberty in general is hammered copper sheets that are formed into and soldered into place as the statue outside surface. They're attached to an assembly or a frame that holds everything up on the inside. Different uses, different looks. Another use is rotogravure plates. Now, this is an old use, not used that often now, but it developed as a stable sheet of material that could be etched into a pattern and then used for printing. Some of them were flat plates. Many of them are round or cylindrical plates that are on rolls for ease of press usage. Artists and others have used these types of applications for years. Generally, it's pure copper, 110. Occasionally, it's a different alloy. But one of the biggest factors to begin with was its availability and its stability. So it didn't change a whole lot, and it held the pattern or the etch that was put on it or in it. We have forged or shaped parts. This is actually the oldest form of getting something into shape. You have all kinds of different forged parts. You have a ladle in the lower center. You have faucet bodies. You have chain links. You have, however, in the center right, you have a hammered bracelet. You could still find those. Again, this is heating the material and then hammering it into the shape using a hammer or a shaped part to get it into the final shape. Wide variety of applications here. I will go to my last application slide. This happens to be antimicrobial applications. This is something that CDA has been involved with for quite a number of years now, and beginning to see some of these applications put into place in healthcare and hospital settings. The materials here can be any of 479 alloys that are EPA registered as antimicrobial materials. The particular property is the antimicrobial property, the ability of the copper material to kill bacteria. Copper and copper alloys are registered with the EPA to kill 6 deadly bacteria, and CDA and its test laboratories have tested it against many other things. You'll see many applications here. There's grab rails, there's IV stands, there's carts, there's door hardware, there's push plates, there's a barbell or a weight, and other. That's only one example. There's other examples. There's a door hardware. There's a light switch. There's cabinet hardware. In the upper left, there's a sink. That is the sink body, or the sink itself, top, is completely made out of copper material. And down on the lower right is a computer keyboard. Actually, the computer keyboard is a very good use. Those are some of the dirtiest things that we actually touch every day. These have the ability to disinfect themselves within a short period of time of infection. In other words, when you put your hand on these, you impart bacteria to the surface. That surface then starts killing that bacteria immediately, and short time after that it is free of bacteria. So it decreases the bacterial load or the bioload in the ambient environment, and therefore it can decrease the amount of infections that are transferred one person to the next person. That's the effect that we're trying to have. The object has to be able to be formed, and many of these applications are made out of copper nickel at least at this point. But one of the requirements for this application is that these have to be bare. There can be no coatings, no plating, no surface treatments of any type. The material has to interact with the bacteria to have this effect. And I believe that's my last slide of applications. Now, I've tried to impart the idea that the properties, the inherent properties, or the physical and chemical and other properties that are inherent in copper and copper alloys have a direct effect on how we use these things. why we use them certain ways. I hope that is helpful. I think it is a third part to what I've tried to do in the first two webinars, and I believe I'll take your questions if you have it.
Yeah, we do. We have some questions coming in. Like Jim said, go ahead and send your questions in. We'll get to this first one here, and we'll get to them. How exactly does antimicrobial material kill bacteria? Is it the actual material, or is it a coating of some sort?
No, there is no coating. It cannot be coated. It cannot be plated. It is the active ingredient that is listed in the EPA registration is copper itself. The copper ions are taken up by the bacterial cells and essentially cause it to malfunction. I could go into details, but it gets rather involved in microbiological speak, if you will. But one of the first actions that happens is it overloads the cell with copper. Copper is a micronutrient that you and I and all living organisms use every day as a part of our intake. We have copper in our vitamin pills. We have copper in our food and vegetables and so forth. We use it in our cells. It helps maintain our bodies. Same is true of bacteria and or the smallest organisms on the earth. So they take the copper in, and if it's a pure copper surface, they have trouble stopping, if you will. The cell gets overloaded. The membrane of the cell essentially explodes. They can't get rid of the copper as well. The first item is the cell basically explodes. That's an easy way of saying it, where the membrane is broached. The cell is overloaded with copper, so there's too much, and they cannot relieve themselves of the copper. And there's a third action which alters the cell somewhat, and they cannot reproduce. So there's three actions, and there may be more. They're still working on that. So no, it's not a coating. It is inherent in the material itself, and copper is the active ingredient.
Does surface oxidation affect the antimicrobial process?
That's a very good question, and we get that asked all the time. On copper alloys, and these are healthcare and hospital type settings, or even for the doorknob at your house, but mostly interior surfaces. The oxidation that is minor on these surfaces over time is not deleterious or does not destroy this particular property. It will still work 20 years from now. So the oxide does not harm the effect. We've tested that.
Okay. And you guys have more information on the website, don't you, Jim? Because I think I've seen on there some white papers and things. If because you said it can be.
Yes, there's a full website, antimicrobialcopper.com, that I didn't put on my slides, but you could go there, and that's a whole separate website just dealing with this particular application.
Okay.
There's scientific papers. There's scientific papers. There's conference papers. There's the EPA registrations. There's a booklet on applications and available hardware or pieces of equipment that are made with these materials. There are suppliers that make these products. Yes, it's all on there.
Okay. We had another question come in. Is an excess of copper exposure harmful to humans? Example, copper pots.
No. We're a little bigger than a microbe or a bacterial cell. We can handle more copper than they can. However, that being said, our system does react to an excess amount of copper. We tend to not get sick. We don't have any adverse effect. We tend to excrete it in a variety of ways. So we get rid of it. In a copper pot, which is the specific question area, such as if you're cooking with it, if you'll note, copper pots many times, old pots don't have a coating on them, but a new pot, say if you buy it at the store, will tend to have an interior coating on the cooking surface. That's usually a tin coating. But there are reasons for using a pure copper pot, which helps reactivity in some instances. Like if you're doing, one in particular is making meringue out of egg whites. If you do that in a copper bowl or something like that, it makes nice higher egg white meringue. So there is a reaction that happens that aids certain things. You shouldn't cook acidic foods in copper, though, like citrus fruits or tomatoes. I would state that.
Interesting. All right, well, we're right about at the top of the hour, so if anyone has any further follow-up questions for Jim, here's his email address, telephone number. Feel free to reach out to him. Again, you are going to receive a survey here in about an hour. If you would, please complete that. Gives us a good idea of, what you liked, didn't like, what you'd want to see in the future from us in terms of webinars. And once you complete the survey, you'll get the slides to today's presentation, which also includes the links to Jim's first two presentations. So if you haven't had a chance to check those out, be sure to do so. Jim, I just want to thank you again. I want to thank our webinar sponsor today, ABC Metals, and thank everyone for joining us. We hope that we will see you at our 63rd annual convention in March. That's in Las Vegas. You can find more information about the convention on our website. And we thank you so much. We appreciate everyone being on the call today. Thank you, Jim.
Thank you.
All right. Goodbye.